Hello everybody, welcome to today's mini lecture on implicit partial differentiation of surfaces. Also the topic for today are surfaces. Let me start with curves. Remember that back in Calculus 1, graphs of ordinary single variable functions are special curves in the xy plane. They are special since they obey the vertical line test. Every vertical line meets the graph in at most one point. We have to think back even further to college algebra to remember that curves are solutions of equations in two variables, like x squared plus y squared equals 1, for instance. This one is a unit circle, and it is not the graph of a function. We cannot solve the equation uniquely for y. Still, we may want to calculate slopes of tangent lines to that curve, and for this we use the technique of implicit differentiation. Now remember that the graph of a multivariable function c equals f of x, y with two variables is a surface. But not every surface can be expressed in this way. The sphere or the donut-like surface shown cannot. Again, the reason is that these surfaces do not pass the vertical line test. Some vertical lines meet the surface in more than one point. Take the z-axis as an example here. So again, a surface is a graph of a function c equals f of x, y of two variables if it passes the vertical line test, where every vertical line meets the graph in at most one point. General surfaces can be described by equations in three variables, x, y, and z. The unit sphere, for instance, obeys the equation x squared plus y squared plus z squared equals 1. The donut-like surface shown obeys the equation 3x squared plus y squared plus z squared plus 0.19, the whole thing squared, equals 2y squared plus z squared. But the surface does not obey the vertical line test. We cannot solve this equation uniquely for c. What if we still are interested in questions similar to some when facing a function of two variables? For instance, 1. Find the equation of the tangent plane to the surface at some point, for instance at 0.242, 0.5, 0.5, shown in red here. Or 2. What is the maximum z-value points on the surface can have? Similar to implicit differentiation in Calculus 1, we will view the surface locally as a function of two variables x and y, and we will use multivariable chain rule to answer these questions.
Why don't we rather look at a multivariable function in three variables?
We do. We take the surface equation and push every term on the left. Then we define a function this way by saying f of x, y, z equals 3x squared plus y squared plus z squared plus 0.19 whole thing squared minus 2y squared minus z squared. Obviously, for every point on the surface, f of x, y, z equals 0. If you just look at a very small piece of the surface, it probably passes the vertical line test. Then the surface can be described locally by a function c equals c of x, y, whose formula we don't know. We would, if we would or could solve the equation above for c, but very often, not in this case actually, this is algebraically impossible. Now look at G from two-dimensional space to three-dimensional space, defined by g of x, y equals x, y, and c of x, y. It takes the projection of our surface part as input and maps it back to the surface part in R3. We compose this with f and get a function f composed with g. This function is actually quite simple, since f of g of x, y equals 0 for all x, y where g is defined. The reason is that g of x, y lies on the surface, and f maps every point on the surface to 0. By multivariable chain rule, version 2 actually, we know that these formulas are true. But since the three components of G are G1 of xy equals x, G2 of xy equals y, and G3 of xy equals c of xy, we have the partial of G1 with respect to x is 1, the partial of G1 with respect to y is 0, The partials of G2 with respect to x and y are 0, respectively 1. And the partials of G3 with respect to x and y are the same as the partials of C with respect to x and y. We plug these expressions into the chain rule formulas and get the partial derivative of the composed function with respect to x is a partial of f with respect to x plus the partial of f with respect to c times the partial of c with respect to x. And the partial derivative of the composed function with respect to y is a partial of f with respect to y plus a partial of f with respect to c times partial of c with respect to y. Since the composed function f circle g is constant, since f of g of x, y is 0 for all x and y considered, both partial derivatives of this composed function are 0. So the left side of the equation are 0. Now we solve these two equations for dc over dx and dc over dy and get dc over dx is a negative, the quotient of the partial derivative of f with respect to x and c, and similar for dc over dy. Here we use the abbreviations f subscript for partial derivatives of f. These equations, which are quite similar to the equation one gets for one-dimensional implicit differentiation when applying multivariable chain rule, are all we need to answer our two questions.
Yes, but we don't need them. Why don't we rather just look at the function f?
Let me just finish our example. The partial derivatives of f with respect to x, y and c can be easily calculated, and they are as follows. Therefore, by the above equations, the partial derivatives of c with respect to x and y are these quotients here. For x equals 0.242, y equals 0.5 and c equals 0.5, plugging in the values we get the partial of c with respect to x is negative 3.437 and the partial of c with respect to y is 0.367. Therefore, the tangent plane has the equation c equals minus 3.437 times x minus 0.242 plus 0.367 times y minus 0.5 plus 0.5, which is equal to negative 3.437 times x plus 0.367 times y plus 1.148. For the maximizing c question, we have to find all critical points on the surface where both partial derivatives are 0. So the three conditions are, first, must be on the equation, on the surface, and second and third, the partial derivatives of c with respect to x and y must be equal to 0. So we get these two equations since a quotient is equal to 0 if the numerator is equal to 0. I leave it to you to solve the system of three equations with three variables x, y, and z. It is actually best to consider the four cases, both x and y being equal to 0, x being 0 but y not, y being 0 but x not, and none of x and y equal to 0 separately. The 8 solutions are 0, 0, plus minus 0.74, 0, 0, plus minus 0.26, and 0, plus minus 0.44, plus minus 0.79, with all numbers rounded, shown in the graph here. We have 4 saddle points, 2 local minima, and 2 local maxima for C.
Why don't we rather just look at the function f? All points x, y, z with f of x, y, z equal to 0 are on the surface, so the surface is a level surface of f. Therefore the gradient is normal to the tangent planes. All we need is the gradient at 0.242, 0.5, 0.5 and for the second question, points where the gradients are vertical.
Yes, very good idea. This is the second way to do this. Before I show how, let me briefly demonstrate why the normal plane of a vector a, b, c has the equation ax plus by plus cc equals d for some d. Why this? Take 2 points x1, y1, c1 and x2, y2, c2 obeying this equation. The vector between these points is x2 minus x1, y2 minus y1, c2 minus c1. Subtracting the two equations, we get a times x2 minus x1 plus b times y2 minus y1 plus c times c2 minus c1 equals d minus d, which is equal to 0. That means that the scalar product of this vector and ABC equals 0. That means that this vector, which is any vector on our plane, is perpendicular to ABC. The gradient of f at this point 0.242, 0.5, 0.5 is obtained by plugging these values into the three formulas as calculated above. We get the gradient of f at this point about 2.514, negative 0.269, 0.731. Then the equation of the tangent plane at this point has the form 2.514 times x minus 0.269 times y plus 0.731 times c equals d, where d can be found by plugging the coordinates of the point in. We get d equals 0.839. So we have 2.514 times x minus 0.269 times y plus 0.731 times c equals 0.839. And we solve it for c and get c equals negative 3.439 plus x plus 0.368 times y plus 1.148, same as above. For the second part, the first condition is that the point must be on the surface, so f of x, y, c must be equal to 0. And the second condition is the vertical gradient, meaning that the gradient has a form 0, 0, something, or in other words, fx equals 0 and fy equals 0. The partial derivatives of f with respect to x and y must be equal to 0. So we get the same three equations as above. Thanks for listening.